In the panel discussion, we heard Alan Kay talk about the value of new architectures for programs, how new architectures enable systems that simply wouldn't be possible otherwise. We've seen that happen already with rule-based systems, with object-oriented systems, with constraint propagation. I expect we'll see more. We heard Ed Feigenbaum talk about the addictive quality of Lisp programming environments, and there was general discussion of how these tools and programming techniques apply not only to AI software, but to conventional applications too. Alan Kay mentioned the broad applicability of object-oriented programming, such as building operating system software. I feel strongly about the importance of the programming techniques and tools that have been developed and used to do AI research and applications. They're proving to be valuable in many programming situations. In a moment, we'll be going to an interview with James Martin on the value of rapid prototyping and Lisp programming environments. The main message to listen for is the value of rapid prototyping, the ability to see working versions of a system in time to make changes. The idea being that as customers see and use the working prototypes, they come to better understand the problem and what would constitute a solution. When I've said that to people outside the computer field, they often respond, "But that's so obvious. Why does that need to be discussed?" Well, if you're in the computer field, you probably agree that the advantages are indeed obvious, but until recently it just hasn't been practical to do it. We haven't had the programming tools necessary to produce prototypes quickly. So desirable as it is, it was impractical. Now that's changed. We do have the tools, such as those collected in the Lisp machine environments. And developers are finding that those tools are not restricted to AI applications, but can apply to conventional programming as well. There's one large corporation, for example, that requires that a working functional prototype be built on a Lisp machine for any interactive application prior to writing a spec, whether it's an AI application or not. Now, I'd like to clear up some possible confusion over terminology. In the data processing field, prototyping often refers to building a series of screen images that show what a user would see if the desired program existed, but there's no functionality behind the screens. They refer to functioning prototypes as exploratory programming. It can be a little confusing, I know, but that's the nature of new technology.
There's an enormous amount of prototyping going on in commercial data processing, and most of it relates to systems where you know what you're building, at least roughly, and you want to try out the ideas with end users and make sure the end users can use them and try out the screens and try out the reports and so on. Now, exploratory programming is an environment where you don't know what the end results are going to be, and so it's more like research. You're exploring what is possible in software development. And that tends to need different types of tools from the mass prototyping that's going on for ordinary commercial data processing.
What kind of tools support that?
For exploratory programming, I think you need the most powerful language you can possibly get so that you can build results very quickly. You're not really concerned with machine performance, but you want to be able to move very fast and doing exciting things and exploring what's possible with computers. The best Lisp programmers build up a personal capability which enables them to do very complex things at a quite extraordinary speed, much more so than the, well, certainly much more so than the third generation languages, but I think more so than the fourth generation languages also. Something is happening in data processing which is going to change the whole way we build systems, and that is the evolution towards CAD, computer-aided design, so that you can design applications on a screen, rather like an engineer designs parts on a screen, and then have a computer which checks the design, makes sure that all the gears mesh exactly, and then generates code from it. And to a large extent, the birth of that happened about 3 years ago with the building of prototypes, exploratory programming. And down in my home in Bermuda, we had Dan Stenger from Texas Instruments and some people from the company which became Knowledgeware And I'd been building rough ideas on a laser using the graphics capabilities to build static screens on a laser. And what I now wanted somebody to do was to take those static screens and make them move, and so build the clockwork into it, if you will. And so the knowledge where people did that in C, and Dan Stenger did it in Lisp. And I was quite astonished at the speed at which he could get very interesting prototypes working in Lisp. He had the ability to do things which with a conventional language would have taken a long time because of the complexity, and he got them working in days. So in a period of about 3 months, he had a very rich set of capabilities in prototype form running. And what is really meant by exploratory programming is that as you see that coming together, you change your ideas about what really works. It begins to look different, and your view of what the end result is going to be can change quite dramatically. And that's why you want a very fast, a very powerful language for exploring what's possible.
As you went through this process and saw the system emerging, did it change your concept of the design of the system?
Oh, it changed my view enormously of how the system ought to be put together. And one of the characteristics of building that was that at the beginning of the process, I couldn't have written specifications for it, where the specifications would have really been very useful, because I hadn't got a clear enough idea of what the end system was going to look like. And so it was very much a process of building it, exploring it, saying, I don't like that, let's change that, let's do something differently. So exploring the art of the possible.
You say that exploratory programming is a lot like research, but not very much of that is done in data processing departments. So where does it fit?
In the average conventional data processing department today, there's almost no exploratory programming. There's almost no research. What's going on is they have a very large backlog of applications, and so they write specifications and then they build applications for those specifications. And you'll very often find a giant DP department of 2,000 people with nobody doing research. And we are now needing to put computers to work in different ways in industry to make industry efficient. So it would make sense to take a certain number of that 2,000 people and say, let's make them a research group where we are exploring new ideas which might become very important, but we're not sure. And so exploratory programming, being rather like a research function, would make sense, I think, in today's commercial data processing environment, as well as in engineering and scientific computing.
So from your point of view, the capabilities ought to be widespread.
I think it would make sense, yes, to get it widespread. There's no question that we do not understand the types of applications which are possible with today's computing power. We know that in factories we want to build a CIM environment, and a CIM environment is going to need an enormous amount of computing, and we're going to make lots of mistakes on the way to creating that environment. And so we'd like to have exploratory programming with which we can build those things very quickly and try them out and see if they work, and probably throw away half of them.
Now, we've been talking about exploratory programming for data processing. What about other types of applications within corporations?
In the scientific and engineering areas, exploratory programming is being much more used today than it is in commercial data processing. There was a system which they describe in IntelliCorp, which was built by 2 NASA engineers, which was designing the environmental control system for a future space station. And these engineers hadn't been programmers before, but they learnt the IntelliCorp toolkit, and in a period of a few months had put together the most intricate and elaborate simulation of the possibilities in that environmental control system. And if that had been done 3 years before, I think it would have taken a couple of years to build simulation that was anything like comparable. And it almost certainly couldn't have been done by those people. It would have had to have been done by professional programmers. And what we really want is the engineers who are inventing to be able to use the computerized tools to help them to explore the possibilities of their inventions. And in companies that make toolkits, they have a lot of people with very creative ideas, and they'd like, when somebody's got an idea, they'd like to say, well, build it, and let's take a look at it. Build it in prototype form, and let's see if it really makes sense when we see it live on the screen. And so you need a language there with which you can build those things as quickly as possible.
We're going to get a little more specific now. We have an interview with Dick Gabriel about the benefits of Lisp and then we'll show you a demonstration of a Lisp machine environment. Following that, we have some comments from people who have used rapid prototyping on Lisp machines. Dick mentions that Lisp is the second oldest programming language that's still in use. Only Fortran is older. What I find interesting about this is that Fortran and Lisp have persisted over the years for exactly opposite reasons. And these reasons might be useful to keep in mind while you're watching the interview. Fortran has persisted because of all the programs that have been written in it that their owners don't want to have to rewrite. As a result, Fortran hasn't changed very much over the years. It's persisted because it's been more or less static for 30 years. Until recently, Lisp hasn't had a body of software to support. Most of the programs that have been written in Lisp were research programs, written to understand how certain kinds of programs might be built. For example, how to build inference engines or natural language understanding systems. Once the projects were done and the lessons had been learned, the programs that were written in the learning process were no longer needed, and so they were discarded. But to help write this experimental software, lots of potentially useful tools were collected and invented and added to the Lisp programming environments. Also, new programming constructs were added to the language itself. So for 30 years, Lisp and the Lisp programming environment have been constantly changing, incorporating what's been learned about programming and applications. So in contrast to Fortran, Lisp has survived because it has not been static. There are some features of Lisp that facilitate the incorporation of new tools and new programming constructs, and you'll hear about those in a few minutes. Lisp has been the language of choice for artificial intelligence research and for applications since the 1950s. Now, a lot of other programming languages have come along, and they've been considered, but Lisp has persisted as the language of choice for the AI community. We're going to look into why that is, and Dick Gabriel is here. He is the president and chief technical officer of Lucid Incorporated. He's also a consulting associate professor at Stanford University. Lucid sells AI system software. Dick, why is it that Lisp has been used so extensively in the AI community?
Well, as you know, artificial intelligence programming is not the easiest thing in the world to do. And part of what the AI community wants to do is to bring the best tools, best concepts, best languages to bear on that programming problem. And as the world of programming has gone by over the last 30 or 35 years, the AI community and the Lisp community has looked at the ideas and the concepts that have gone by and picked up on the good ones and thrown away the bad ones. Lisp today is very much different from what it was in the 1950s, primarily because all of the good ideas, or many of the good ideas that have gone past, have been picked up by Lisp, including programming tools from other sorts of areas.
What are the aspects of Lisp that contribute to its flexibility?
Well, there's certain technical aspects of Lisp that give you these possibilities. One is there's dynamic runtime typing. In other programming languages, variables are typed. That is, when you see a variable and you see a declaration, you know what type of object it must be referring to. In Lisp, when you create an object in memory, which is something that Lisp is very good at, when you create an object in memory, you can examine that object and see what type it is. That is to say, the type is encoded with the object rather than with the variable that refers to the object. Because the typing is done at runtime instead of compile time, that's an issue you don't have to worry about to get your program to run for the first time. Later, if you want to go back and eliminate that type checking at runtime, you can do that. But when you're doing rapid prototyping, the flexibility of being able to create an object, have it persist for some length of time, be able to reason about it is I think, a very important aspect of programming rapidly. There's dynamic linking of functions and separate compilation. Those are related. What this means is that you're able to write your programs completely separate from each other. That is to say, if I'm programming part of a system and you're programming part of a system, then all we have to agree on is the conventions. When I'm compiling my code, the compiler doesn't have to see your code. And what happens is, when these two pieces of code are loaded into memory, there's a dynamic linking of the two functions, so that if one calls the other, then this can be done through a one-step process, or an additional step process. What this means is that there's a space between a function and another function which is called, and you can use that space to load in new functions, to define new ones, to encapsulate the second one, to put debugging information or breakpoints between the two. One of the aspects of Lisp that has been of extreme importance, I think, over the years is the very flexible macro facility, which has enabled people to write abstractions that separate implementation of low-level details from their use and enable the resulting program to run fairly efficiently. I think that macros as defined and used in Lisp are one of the sort of underrated aspects of the language. Other things that have helped make Lisp such a congenial environment for programming and debugging is automatic memory management. In other programming languages, you can either stack allocate objects so that when you call a function, some space is allocated on a stack, the space is then used, and the function returns, the space is reclaimed. In Lisp, what you do is you create an object with an explicit constructor which builds such an object. This object persists in a thing that's like a database, and then when that object is no longer in use, it's garbage collected away.
Now, most of the aspects that you've described have to do with flexibility, but what are the trade-offs between flexibility and efficiency?
Two things to be said there. One is, do you always have to pay for the flexibility, and how important is the flexibility? The more difficult and more complex the programming task you have, I think the more important the flexibility is. But once you've developed your program and you're fairly confident that it works well through testing or verification or other techniques, then you want it to run fast. Up until the late 1970s, Lisp has been a very slow language with respect to other languages. That is to say, if you wrote the same program in Pascal or C versus Lisp, you'd see factors of 5 and 10. Over the last 10 years or so, we've seen compiler development going on. We've seen specialized hardware developed that have closed the gap in efficiency, so that when you're done with your program, you go back, you declare all your variables just the way you would with Pascal. You go back and you use static subroutine linking rather than dynamic subroutine linking, and you can buy back much of the efficiency loss. You can go back and eliminate almost all of the runtime type checking that goes on, so that rather than factors of 5 or 10, we're looking at factors of 2 down to percentage differences in the efficiency of running Lisp code.
Okay, great. Thanks a lot, Dick.
No problem.
The main programming technique that's been used for building complex programs quickly is incremental development. Start with an overly simple but working version of the desired program, then elaborate pieces of the program one at a time. At all times, the programmer is dealing with a functioning system, so he's getting strong feedback on the value of each change he makes. He can try it out and decide whether it was a good idea or not. And at each step, he's making understandable modifications to a confined part of the system. In this way, he can sneak up on complex problems one simple step at a time, never having to confront the complexity directly. Some of the features of Lisp that Dick Gabriel mentioned bear directly on incremental development, especially dynamic linking, incremental compilation, and the fact that Lisp treats programs as data. Because Lisp programs can be manipulated as data structures can be manipulated, it's been possible to build lots of programming tools for Lisp. Think about that for a minute. If you're programming in BASIC, that BASIC system probably came with a trace facility, a debugging tool for watching which statements are being executed as the program runs. If you want to write a better trace facility in BASIC, well, you're just out of luck. BASIC programs cannot be written to manipulate other BASIC programs. They're not treated as data. But in Lisp, you can write a new trace facility, or an enhanced single stepper, or a program inspector, or a function locator, or a program formatter, or a better debugger. Over the 30-year history of Lisp, lots of programmers have written lots of tools to help them program more productively. Lisp machine programming environments are collections of the best of those tools. They're built to help AI researchers in their explorations, and now that they exist, they're proving to be useful for other kinds of applications as well. So these programming environments offer a lot of power today, and the features of Lisp that brought them into being are still there. The knowledge engineering toolkits are examples that new tools are still being added to Lisp environments. I expect that the programming environments will continue to improve. Here's a look at one. Dick Gabriel spoke of several aspects of Lisp environments that make them good for prototyping. We're going to give you a demonstration of a Lisp environment on a Lisp machine. Rusty Lewis is from the Computer Science Center here at Texas Instruments. Rusty, show us something about the Lisp environment.
Okay, this application is called the Coordinator, and it's a VLSI CMOS compactor. First thing I'd like to show you is a Lisp utility called the Peak processor. I'm choosing Windows, and this shows you a list of all the windows in their hierarchy that I have in my memory. I'm picking the design editor, which was the frame that you saw before, and I'm going into the inspector.
Now, you wrote a big part of the design editor, but if you were just a user of that and wanted to modify it, you could be going through the same process of going from the application to the Peak utility to find out where the code is that defines that system. That way you can modify it, debug it, whatever you need to do.
That's correct. In Peak, I have a listing of all the windows, all processes, and I can pick on those and go to the editor or go to the inspector or any of the other utilities. So now I'm in the inspector, and I'm going to pick the graphics window pane that you previously saw on the screen.
The inspector is a utility that allows one to take a look at complex data structures, move through them, change values, find out where different pieces of them are defined, and so on.
Okay, now I'm going into the editor, and I'm going to meta point or edit the definition of a function that I'd like to change.
The way that Rusty got to the editor from the inspector was simply by pointing at the name of the function that he wanted to edit. The system put him into the editor at the location of this function that he was going to edit. Now, the important point to note here is that this level of integration between these tools greatly increases the programmer's productivity. He doesn't have to keep these things in his own head. He simply points at them, moves around through these display-based tools, and quickly moves from one tool to another.
Okay, this region I've selected is a function that I've previously modified, or a method I've previously modified. And I'm going to go ahead and incrementally evaluate this now using Control-Shift-E.
This incremental evaluation and incremental compilation, which he's going to be doing in a minute, are extremely important aspects of the Lisp environment. If a modification is made to the system, the entire system doesn't have to be recompiled. Just that small function or the small piece that's been changed can be recompiled, and then that recompiled piece can be added into to the entire system and have it run that way. Again, that greatly speeds up the process of change and debugging and significantly increases the productivity of the programmer.
Okay, the change that I just made is a change to the way that these transistors and wires are displayed. I should be able to toggle them and show them in a symbolic way, which is that, or a geometric way. At any time during this development process, back in Emacs, I could have hit Control-Meta-Break and gone into the window debugger.
What the debugger does is allows the programmer to take a look at the dynamic state of the computation. In that way, the programmer can find out what the history of the calls and the values of variables and so on are in the computation, modify them, and then go on from there.
Okay, in the Windows System Debugger, I have an inspector pane, a pane for the local and special variables of the current stack frame. I have the arguments for the current frame, and this is a history pane. I can move up and down in here, and as you see, as I do that, the arguments change. From the debugger, I can go into the inspector. I can look at documentation string. I can go back to the editor and edit the source code of any of these functions or methods or macros, just like a meta point. And I really don't, I can do this from running a program that I've never seen before. I mean, I can go in there and see the execution history, so I don't need to know that much about an application if I want to go in and do some modifications.
You were a Pascal programmer before you started using these Lisp machines about 2 years ago. What do you see as the difference between your productivity in Pascal and your productivity on a Lisp machine?
Well, it's been my experience, or at least my own personal feeling, that what would take me a month to do in a more conventional environment, I can do in a week or less on a Lisp machine.
Thanks, Rusty. What we saw in this demonstration are some of the aspects of a Lisp machine environment that make it so useful for rapid prototyping. We saw Rusty find the code that defines an application, then go into some of the powerful tools on the Lisp machine to modify that application. What's most important about these tools is their high level of integration. It's very easy to move between the tools, and also very easy to move large data structures between the tools. We saw an example of incremental compilation, which allowed him to make a small change to a large system and see the effects of that change right away. Now, we had limited time, so we could only see a few of the functions that are available in the Lisp machine environment. For example, the editor has over 700 commands that are specifically designed to help programmers. The system as a whole has over 10,000 functions in it. What all this adds up to is a system that greatly increases the programmer's productivity. What this means is not just that the programmers end up creating more lines of code faster, but they have more time to consider more options and more opportunities. What that means is that they'll end up with a better design. At CRI, a Danish software firm in Copenhagen, I talked with project manager Erik Heilmeier. CRI prototypes systems on Lisp machines even when the system will be delivered on conventional equipment.
It's very fast to get a prototype and an amplification or an exemplification of your ideas, your concepts up and running, so you can check them, you get a much better feel for them. Because you don't have to go through the steps that you have in normal programming, writing down the code and so on. This type of development system supports that easily. Another thing is that it's much easier to maintain the systems because they are defined as objects, what's called the object-oriented approach. You can delete objects, you can modify objects, add new objects. It's much easier to change code. You know exactly what effect it'll have on other parts of the code. Another thing is that the programming formalisms you use here are very close to the way you formulate knowledge yourself. When you do knowledge and knowledge engineering, you normally formulate it in a pseudo-logical fashion as like if-then rules, and these can almost immediately be input to systems like this, so you skip another step in programming. That makes it easier to do, it makes it easier to understand, easier to maintain, and that also reflects on the interaction with the users, because they can much easier see what's actually going on in the system and getting a feel for what the knowledge you extract for them is being used for and how the whole system works and what's good and what's bad about it.
We discussed rapid prototyping at Dornier on the shore of Lake Constance in southern Germany. While they're best known for their aircraft and spacecraft, they're also involved in management information systems. They told us that several years ago, they made significant productivity and quality improvements by prototyping with database systems. Today, they're prototyping more complex systems using AI techniques. We talked with Wolf Vogel, head of the Department of Knowledge-Based Systems.
The basis for this project was started 1 year ago. The basis for this project was our experience in coming up with management information systems, developing management information systems. This we started, I think, 6 or 7 years ago, and with a conventional approach to those management information systems means talking to the guy who wants to have a management information system and producing paper. As a result, and you have this half-meter paperwork, you know, and the normal way is that the user has to sign this as his requirement in 1 week or so, you know, about that. And obviously, the user can't really say this is a definite requirement, because he can't read half-a-meter paper in a week or so. And the final result is that the industry develops on this half-a-meter paper, and at the end both are disappointed, the user and the engineer, because the user isn't satisfied with the product, and the engineer did the best but failed because of the not verified user requirements. And this was our reason why we started research in the area of prototyping for those conventional management information systems.
Some years ago, you did a rapid prototyping approach for management information systems oriented around databases.
This was the first approach, because management information systems, the essence of these systems is a database with a user interface. And we thought it would be a good idea for research to start with management information systems as a prototyping tool. Yeah, not as a final system, but as a prototyping tool, in order to clarify and verify user requirements on this database based management information systems. And we found at least that we can reduce the time for installing a prototype up to 1 man-month. And when we compare this to the conventional approach, we must say the conventional approach took about 48 man-months, about that. Can't say exactly, but this range, I would say.
Now, recently you've gone to a knowledge-based approach. What are your reasons for this?
Yeah, the reason is that we expect from the future management information systems we have to build in the next years will demand for more functionality, like selecting data in an intelligent way, like preparing decisions. And this we can't do with a pure database management system. And therefore, we feel that we have to research AI techniques using for requirements engineering for those more AI functioned information systems we expect in the future. And within this project funded by the European Commission, we try to get the user in the loop of the design by saying for the first attempt roughly his requirements, because normally it's really for a user difficult to imagine what requirements he really has on an information system, imagining that he will be computed by a computer, supported by a computer. He only can imagine his today paperwork and will make from this his requirements. And therefore we feel it is necessary to give him not on a complete specification, but on his first impression, his view on the system. Yeah? And this we want to do, expecting a development time for a first prototype within 1 or 2 months, about that. And I think, in comparison to our first example with the database management system, that we have otherwise to expect a development time of this kind of knowledge-based information systems about 36 man-months, at least I would say. By the way, this AI techniques I mentioned before means that we use the TI Explorer with a key on it, and the essence of our work is to implement a application area concerning this office environments on the key tool. That's the essence of our work.
Renee Barling is the project director of Applied AI for the Equitable Life Assurance Society. The Equitable has worked on knowledge-based systems for many financial applications, including risk assessment, life underwriting, cash trading, and investment management. I spoke with her in San Diego at a Gartner Group conference on AI as applied to corporate information systems. Are there a lot of applications in the financial field for this technology?
I would think there are an unlimited amount. Because there's two ways you can use the technology. You can use it to solve brand new things that you haven't even addressed before. But you can also use it to enhance existing applications. And there are many financial applications out there that could be brought another level of sophistication. So, I mean, if you talk about, well, everybody's working on a trader's workstation. We talked about that. But portfolio analysis, foreign exchange, the options market, I guess. In insurance, there's claims adjudication, but there's also claims analysis, healthcare cost containment. I mean, just loads and loads of potential applications. In the banking industry, there are many applications, too, that are suited to the technology.
Tell me about the process of prototyping these knowledge-based systems.
We started out with a risk assessment system for internal audit and using our philosophy of taking the most subjective factor first, we chose the management risk because it was very subjective, and we modeled that from the bottom up. When we proved the feasibility of doing the system, it was decided both by the business area and ourselves that they wanted a deliverable in a short period of time. So we expanded the number of risk factors. We didn't go in quite the depth that we did for the management risk, but we have a system now that's operable. And that took many iterations of going through and refining things, showing it to them, getting their approval, then showing it to other experts in the field to get some kind of conformity before we could say, well, we have now an operational prototype. An operational prototype is one step before putting something into production. Although these systems are never finished, they still require maintenance.
In going through this process, you were using incremental development. How important is that?
Well, it depends. Again, if you could capture it all up front, it'd be wonderful, but it's just not possible. So you capture it in pieces and keep building on those pieces until you have a robust enough system that actually can stand up in a production environment.
Mm-hmm. Now that's one kind of prototyping, the kind where you're gathering the knowledge base. What about the user interface?
Okay, that also is a function of refinement, but usually when we do our knowledge elicitation, okay, we take tapes, at least initially when we really don't understand the problem domain. We tape the interviews, and then we have them transcribed. And then we go fastidiously through these tapes, pulling out different pieces, pulling out the actors, which are the people that perform the tasks, the timing involved in doing the tasks. But also out of that falls pieces of an interface. I mean, the interface itself, there's something that the person using the system is going to take an action. You have to know what those possible actions are and where to put them. Then you have a structure. Structure is usually from the problem domain itself. And again, in the case of the internal audit system, it was a hierarchy of what we call lines of business, strategic business units, and auditable units. It was a hierarchy to select from. And in addition, there is a place in one of the panes where an action is taken. In other words, the system has reasoned with something and it's coming back with a result. And then there's another part of that whole environment, which is the explanation, which feeds back to the user of the system in their language exactly why this recommendation was made. Now, those things are in every interface. What you have to figure out is the way the people work. What is the best way to place that on the screen that will make it comfortable for them? Mm-hmm. How intuitive can you make the system?
In your experience, have you found that those people are highly productive?
5 to 10 times more productive, because you're a single user system, you don't have a response time problem. You're also in an environment that's literally seamless. So you go from the debugger into the programming language. You have incremental compile, so when you want to change something, it's snap and you can run it. It's a whole different world than working in the conventional environment.
There's really nothing like the Lisp machine programming environments, whether ours or our competitors. If the field is new to you, An inexpensive way to become exposed to at least the new programming techniques, if not the full environments, is to start out with PC-based systems. Of course, there are the PC-based expert systems shells, such as our Personal Consultant Plus, and there are others, for rule-based programming. Alan Kay mentioned some implementations of Smalltalk for personal computers that give you an appreciation for object-oriented programming. Here's another approach. Get this book, Structure and Interpretation of Computer Programs by Abelson and Sussman, and a copy of Scheme, a dialect of Lisp for PCs from TI. Now, I'm not just saying that because TI sells it. It's affordable, it costs $95, and it's the dialect used in the book. The book will have you implementing and using object-oriented programming, inheritance, rule-based programming, and many more sophisticated techniques very quickly. It's the best avenue I've seen to come to a quick but deep understanding of what these new programming techniques are all about. But please bear in mind that what you'll learn on the PCs is the programming techniques. Powerful as they are, they're only half the story. The other half is the programming environments, and they simply won't fit on PCs. Besides, those environments are designed to improve the productivity of expert programmers. As Alan Kay mentioned, they're not appropriate in price or complexity for a beginner's introduction.
Well, a big problem I see coming up is the integration of knowledge-based systems with traditional data processing, in particular making a very good link to the databases and to the existing programs so that we can begin to do knowledge-based applications in high-volume transaction environments, and that does not exist today.
Well, I think it's beginning to exist. As a matter of fact, today we are, in the more mature systems, we are starting to see systems that access large databases that take in data in real time, that work over networks, that do all the conventional stuff.
Who's going to do that?
Well, the FRESH program, for example, is a perfect example of a system that was built around an existing database, an existing command center. They weren't going to redo their data.
Well, most of your stuff is built around existing databases, right?
Absolutely. I mean, actually, the stuff, one of our most important programs in terms of real use is a program which reads interbank monetary transfers. And what's happened is that people devised a system for how you send messages back and forth bank to bank, but no one will use it. So they've got people reading the messages in English and then coding them into this form that then actually makes the money transfer. So we're talking about computer, person, computer, which is idiotic. So what you want to do is obviously replace that in a link. And the interlink is the ability to read a sentence, a 1 or 2 line thing, maybe 30, 50 words, saying what bank gets paid what amount of money from whose account in favor of what, da-da-da-da, written often in half in English and half in French and whatever else, but it's always about the same subject. From an AI point of view, the reason it's doable, and I think the major thing you can say about AI to the general public, in order to get them to understand it, is that everything is doable if the domain is really narrow. And what goes on there is that that domain is very narrow. You don't ever talk about anything but transferring certain amounts of money to certain banks. Little kinds of complexities show up, but never anything horrendous. As a result, these things can actually work in real live banking systems and are actually doing that as I speak.
I think in the management information systems area, we've seen some surprises. One of the things that was not understood in the academic world as the technology was developed in laboratories and transferred into an industrial setting was the need for a seamless integration with databases. It's just not encountered in academic settings. We don't think of massive databases as being the need to operate upon them. The other thing I think that, and so that technology is actually getting developed by the AI or the knowledge-based systems industry itself. I think the other thing that we didn't understand was the reluctance of the management information systems people to run their knowledge-based systems on detached workstations which are networked into mainframes managing the database. For some reason, the MIS people believe that they actually have to run these expert systems on their existing mainframes integrated with everything else. Now,
There's
That may or
very
may
good
not-
reasons for that.
Well, it
I'll
partly
be
has
happy
to do
to
with-
expand on that if you want.
It partly has to do with the fact that that the technology was not well developed for a smooth coupling between expert systems running in one machine communicating with databases running in a mainframe machine. And it partly has to do with the fact that they would like to exploit computer cycles in mainframes that have been already purchased, as opposed to buying adjunct pieces of equipment, which is what I thought they would have done. I thought they would have not wished to burden their mainframe with the cycle load of the expert systems. They'd be just as happy to run in a Lisp machine or other capable workstation communicating to the mainframe, but they haven't.
Fallacy of Grosch's law, right? They think there's economy of scale.
There is.
The cycles are cheaper in the smaller machines than the bigger machines.
That's exactly right. One of the things which I observe is that people will prototype an application on a Lisp machine and take X months to do it, and then take 10X months to report it in a quote-unquote conventional language so that it runs quote-unquote more efficiently.
Well, I think you're missing a few problems which lead to this, why they do this. First of all, if we talk about the sort of applications that Roger and I have been talking about, you want to begin to support lots of users, and I'm talking about hundreds and thousands of clerks, and you're not going to deploy $50,000 workstations. You're going to deploy that application, deliver that application rather than develop it. You're going to deliver that application basically on a very cheap, almost dumb terminal, basically. That's the preference of a lot of the commercial users. There's another little problem of security. If I've put the underwriting rules of my insurance company in a computer system, and that's what I think distinguishes me as an insurance company from somebody else, I don't want that on some PC, which somebody can pick up and walk off with. So I've got a tremendous security problem. Cost performance we've talked about. There is also a maintenance problem too. You better figure out how to maintain that with not in 1,000 workstations. There's a problem there. If I can maintain it with non-PhD level people on a large mainframe, that becomes very attractive. Maintenance in the sense of updating the rules as they change. And reliability also becomes very key. We're now moving into applications which are more important than payroll. If the payroll goes down, if you can't do that, I can do that I have to do it only by Friday or Monday. It's not catastrophic. If I'm supporting the people doing bank loans in my bank and the system goes down, that person is essentially out of business. So the real reasons for doing that, why the MIS shops want it that way rather than distributed, as you might.
Yeah, but lots of it's just holdovers because the cost performance isn't really what you're saying anymore. You can buy machines that give in excess of VAX performance for a few $1,000s now, and you can...
That may be too large. I see users who can buy terminals for $1,000 and under. That's what they want.
I think it's too large a cost if the user interface is too hard to deal with. So I think having a lot of cycles go into user interface for people who are spread around is very important. And I don't think that there's cost performance in the cycles at all. And when your mainframe goes down, your whole system goes down. When a workstation goes down, only 1/1000th of your system goes down. So I think that even in reliability, and even if you have a lot of the independent machines in a centralized place for security, I don't agree.
Well, I think from the point of view of the industry, one ought to delineate the two big market segments. The knowledge-based systems have been sold primarily up till now into the segment of professionals who are able to cope with the new technology on their own, particularly scientists and engineers. The bulk of the money in computer applications is not controlled by the end user scientist and engineer. It's controlled by the management information systems shops. And those people are accustomed to, and their territory involves, corporate territory involves, large corporate mainframes and large corporate databases. If the industry wants to move into the place where the big bucks are, if there are any people listening to this who are the entrepreneurs of small companies, they better be prepared to do this seamless integration through mainframes onto databases, because that's where the big money is.
That's a sociological issue, not a technical one, though.
It also helps to explain why a lot of the PC-oriented systems have been sold. The scientists and engineers have not had to go through the corporate bureaucracy to get the money to buy PCs on their desks, or they don't have to do it to get PC software. And so they gravitate toward the smaller systems that they can handle on their own. They learn the technology and they do an application or two. We see a lot of those sales.
In the roundtable, we discussed whether knowledge-based systems were integrated with conventional computing, particularly with the massive existing investment in databases. Herb Schorr said it was a major problem yet to be solved, and I and others said that it was already happening. George Heilmeier mentioned the FRESH project as an example, and you'll see a piece on that system in a couple of minutes. But is the integration there or not? The answer is both yes and no at the same time. In fact, one can find an ever-increasing number of systems that are nicely integrated with databases and the rest, and with each one that's done, the next one will be that much easier. But Herb is right too. The job is far from complete. The connections between knowledge-based systems and existing computing facilities are often custom-made. For example, the FRESH system ties a knowledge-based system and natural language interface together with a large existing database and other components. Most of the development effort was spent not on the knowledge-based system, but on getting all the software pieces to talk to one another. As much Lisp code is devoted to the communication between modules as is devoted to the knowledge-based system. There's a lot of ground to cover between the ability to do customized interfaces and a level of integration so complete that customized interfaces are no longer called for. We aren't there yet, but we'll get there because though it may have sounded like a dispute around the table, there was an important thread of agreement. The integration of knowledge-based systems with the existing base of computing facilities is a very important practical problem. Not necessarily a difficult one, but one that must be and is being addressed. We have a few illustrations of what we mean by the convergence of AI technology with conventional computing technology. Canadian Pacific has about 1,300 locomotives like this one. They cost $1.4 million each. They travel 100,000 miles per year for 35 to 40 years. Of course, they want to keep them on the road, not in the maintenance shop. But if a bearing on a crankshaft should fail unexpectedly, not only will it stop a train in its tracks, but it will cost $250,000 to repair. So CP Rail analyzes engine oil for impurities to monitor bearing wear inside the engine. An expert system interprets the results and recognizes when a bearing needs to be replaced. But what I think is most interesting about this application is that it's almost invisible. Data streams out of the spectrometer through a PC and is uploaded into a database on a mainframe computer. Before the expert system, the historical data on the mainframe on a particular locomotive would be analyzed manually to judge the progression of wear. Now, the expert system analyzes the data and presents the user with its conclusions. There are no lengthy dialogues with the user, just conclusions and the ability to ask how those conclusions were produced. So the expert system is not a standalone device, but a component working with other components, the spectrometer, the database, statistical routines, and together they're more powerful than any one could be separately. Next we'll hear about the FRESH system, a knowledge-based system that interprets force readiness data in light of missions, priorities, and schedules in a naval command center for the Pacific Fleet. It works in conjunction with a large existing information system. Here are a few things to watch for. First, the simultaneous improvements in both productivity and quality that result from the use of FRESH. This is a common theme. Second, the way Fresh integrates AI technology with conventional computing technology. And third, why it's so important to build this sort of system. There's more information available than can be effectively used, so AI technology is needed to sit on top of the pyramid to organize and explain problems and alternatives for human decision-making. The reason that the Roundtable members agree that integration of AI with conventional computing is so important is because these problems of complexity and information overload are not peculiar to the Navy, but are pervasive in large organizations and in complex activities. Knowledge-based systems like this one have been shown to be an effective solution. FRESH is a knowledge-based system for naval command and control developed for the Strategic Computing Initiative. In the past, most knowledge-based systems were driven by question and answer dialogues between the system and the user. More mature systems, like FRESH, integrate AI technology with conventional computing technology, such as real-time data acquisition, databases, networking, and graphics.
The command here has 300 or 400 ships, plus several hundred squadrons of aircraft and innumerable people, all under its control. And yet it's expected to use all of those resources in the most cost-effective manner. We've got all those resources and we have a lot of missions that we have to fill. And those missions are defined by the President, Joint Chiefs of Staff, whoever. And so we're required to fill those, and you've got a lot of considerations. You need to worry about how much fuel you're burning. You need to worry about having ships available to fill the next mission. You need to worry about the readiness of a unit. In other words, in fact, can he fulfill the requirements of the mission? And we have to worry about the people. How much time have they spent at sea? That's a very difficult equation. To add all those together and come up with the ideal solution is just a classic problem. It's almost impossible to do for one man to consider all 300 ships and come up with the ideal solution.
FRESH stands for the Force Requirements Expert System. It's a first phase of a command and control system to be built by various contractors for the Fleet Command Center in Hawaii. The system is to basically try to make sure that the right things, the right ships, planes, material, supplies, are in the right places at the right time. The corollary of that is as the world behaves, as things break, you have to make adjustments, either send a replacement or change your missions or something else like that to adjust to the changed conditions. What that meant for the expert system was that it would monitor the fleet message traffic.
We process somewhere between 1,000 and 2,000 messages a day, which all have to be read by human hands and human eyes. And FRESH reads those things and looks for key information, and if it's there, it alerts us. So that's a fairly powerful tool. At this point, we're working to improve it so that it alerts on all the right things, and that's a concern. But just the capability of looking at that amount of data and picking out the high points so that you can walk in at the beginning of the day, do a quick review of the high points, and then if you need more information, it will allow you to access it immediately. Or conversely, you can take the information that FRESH gives you and go back and look for the message. But it has extracted all of the important information from that message, and it's all available for you to recall it at a moment's notice.
As various reports came in, it would try to determine how significant a given message was and whether it needed to worry about it. If it did, it would generate a significant event report and alert an operator, the watch operator on duty. If the watch operator decided that he thought it was also significant, he could ask the expert system to generate alternatives of how to get around the problem. And these could be anything from ignore it to at the far end, change a ship's schedule, an alternative ship's schedule, to go replace a broken ship. The expert system would then, from these potential alternatives, would go determine what the impacts on the fleet and on fleet resource usage, what the impacts would be of implementing any one of these alternatives.
What normally happens is we get a message that a ship has had a casualty or is unable to fulfill a mission for whatever reason, and a determination is made whether that mission is important enough to require a replacement. And if it isn't, then you go along and you make some schedule changes to account for that. If it is a mission that requires a replacement, then the current ops officers will then begin screening ships for replacements. And they have to look at such a rather incredible list of possibilities. To replace a destroyer, there are probably 75 to 80 candidates at any one time. What they will normally do is immediately eliminate 70 of them by general good feeling. In other words, it's a quick scan the way a human being normally does it, and just tries to throw away as many as he can to get down to a manageable number, because a manageable number for them is probably between 5 and 10 ships maximum. They then have to apply all the rules, all the policies, and look at all of the schedules for each of those ships to make sure that they're not causing a problem with some other fairly important mission. That takes somewhere in the area of 5 days to 10 days maybe, but week's what they normally operate on. Obviously, in some cases it's a very easy problem. For a carrier, quite often there's only 1 or 2 viable candidates. But when you start looking at the escorts, it becomes a much more complex problem. So the most recent incident we had, it took about a day for them to pick out the carrier they wanted to send, and it took them about a little over a week to decide on which 2 escorts. We started the problem one night at about 9 o'clock, and by 4 o'clock in the morning we had answers. And we had not limited ourselves to looking at 5 ships. We looked at approximately 40. We did screen out a lot of ships. We didn't look at all of them because we had some rules that were given us that eliminated about half the ships. And so that was very good from that point of view. We were able to make it an easier problem for the computer. So it took us 5 to 7 hours to do the comparisons on 40 ships. We came out with essentially the same answers as the humans did. I say essentially because we considered a lot of ships they didn't. And so we had some ships that were very well ranked that they may not have considered. Now, what we never expect to be able to do is rely on the computer to make the final decision. Because in reality, if you look at 40 ships, the top 5 or 6 are probably very closely matched. And there's some things in there that at this moment you may want to consider very strongly or not. So what we hope to be able to do is look at all of the possible candidates within the constraints that we're looking at, and have the computer make all the calculations and come up with the top 5 or 6 candidates, and allow the current ops officer then to consider the concepts he's worried about, as opposed to applying all the rules and making all the calculations. And from that point of view, the expert system does an excellent job.
Fresh is perhaps unique. At least it's one of the first systems that is being melded within a network of already existing command and control information systems in a classified military environment. And it's important that Fresh be a part of the existing installed base of systems because of the tremendous investment that's been made in those systems. So really it can be viewed sort of as a pyramid where the investment over the last decade has been made in obtaining and processing information for data management and display. And And Fresh and its other systems within FCC battle management program sort of form the top of the pyramid for decision aiding, which is something that we're just getting into as a result of the battle management program. If you could envision Fresh as being an ensign, you know, starting out his professional life, or her professional life, Fresh knowledge base is really in that mode right now. And as we improve it through experience, the Fresh knowledge base will advance in capability, much like an officer who is advancing through his career. So unlike an officer who we bring on board, train intensively, and he becomes a functional expert over a period of several years, we won't lose Fresh. Fresh is, as we see it now, provides about an order of magnitude or better improvement in time in developing a solution to a problem, with the added benefit that it gives us a consistent problem solution, which you don't always get with people. So as we improve the knowledge base again and bring that knowledge base from an ensign to a lieutenant commander and on the line, we'll have a much faster response, but a consistently accurate one.
We've gotten to the point where we've got a very short time to make decisions, and we've got an incredible amount of information available, and you just can't use all the information available unless you've got an expert system that's sifting through it and finding out and letting you know what's important. You know, I guess back in Nelson's day it was a lot easier. All he had to worry about was the ships he could see on the horizon and the ones he heard were coming, and that was about it. He didn't have to worry about a message coming from the king telling him to change course because the message wouldn't get there in time. So he had a very small problem, and he handled it incredibly well. Now we're capable of communicating an awful lot of information back and forth, which makes, hopefully, the final decision will be a much better decision for having all that information. But without some help, you can't use it. And that's where the expert systems have to come in.
We've covered a lot of ground in this symposium. We started with knowledge-based systems. They're being widely applied, so widely, in fact, that corporations are treating this as a strategic technology applicable throughout the company. They're organizing corporate activities to best take advantage of it for improving productivity and for new product opportunities. There's plenty of work left to do. The Roundtable mentioned some of the untouched opportunities and current research directions. And the work is underway that's needed to realize the clearly seen needs for real-time and embedded knowledge-based systems, and for integrating AI technology with conventional computing technology. Natural language technology. Wouldn't it be nice if computers understood whatever we said to them and could read through all that written material that we find it hard to get to or forget by the time we need the information? That'd be great, but it just doesn't exist and isn't likely to for quite a while. I've been encouraged over the last several years by the search for solvable problems for natural language technology. Cost-effective systems are appearing for narrow domain applications, and engineering discipline and adequate technologies for natural language interfaces and text understanding systems are emerging. Programming techniques and tools. If you've never used a Lisp machine programming environment, you might be led to believe that using Lisp and programming tools on PCs or on a Unix workstation is about the same as on a Lisp machine. Lisp is Lisp and tools are tools, right? Well, look at it this way. I have a drawer in my kitchen with a hammer, screwdriver, a few screws, nails, and some other stuff in it. If I want to hang a picture on the wall, that's all I need. But walk into a master cabinet maker's shop and you'll see tools you may not even recognize, specially made for special jobs. But if the cabinet maker is just going to hang a picture, he probably uses the stuff out of his kitchen drawer. However, with the special tools he's got and the skill he's acquired to use them, he can create things of value and beauty that just wouldn't be possible without them. So if you're just doing simple programming, like a lot of other programs you've written, don't bother with a Lisp machine. On the other hand, if you need to puzzle out how to build something that's never been built before, or you think there's merit in the idea of programmers and users working together on functional prototypes, well, a lot of people who have used Lisp machines won't use anything else. The last thing I want to show you is from the interview with James Martin. We met in San Francisco to talk about prototyping, but at the end of the interview, we were talking about AI in general. Luckily, the camera was still rolling, and we captured some interesting advice.
Data processing managers out there should understand that there are many commercial applications of expert systems, really an enormous number of applications, many of which are likely to affect the bottom line in the corporation, affect the capability to make decision support systems in an organization, the running of a factory, the introduction of computer integrated manufacturing is going to be strongly affected by rule-based processing and artificial intelligence techniques. The researcher out there, there's a vast new world which has opened up. We have no idea where the technology of neural nets, ultra-parallel machines, artificial intelligence on ultra-parallel machines, we have no idea where that is going to take us. So the opportunities for new research, for new PhD studies is gigantic. The mechanical engineer making mechanical devices, household devices of all types are going to become more intelligent. They're going to have lots of rules. It's cheap now to put 1,000 rules into a mechanical device. What is it going to do if it has 1,000 rules? And every engineer ought to be trying to think what he can invent if he can put that type of electronics into mechanical devices. So there's just a vast number of applications. The programmer out there should be saying, if you're a programmer, how do you earn a very high salary 5 years from now? Well, if you can do very powerful things, learn very powerful tools, how can the artificial intelligence toolkits enable you to build things much faster, build much more complicated things? What could you do if you use the software from Art or Key instead of using COBOL or Fortran or Pascal? I think we're on the brink of almost the birth of a vast new industry. If you looked at computing in 1980, it had become rather conventional and people thought that they knew everything. But now we know that we can build ultra-parallel machines, machines with 1 million processors, like the connection machine, and only more so. We know that we can build neural nets. We don't know what the applications of neural nets are yet. We know that we could build a neural net on a chip, and we could then have 1 million of those chips, like in a connection machine. Now, what are the applications of that? Nobody knows, but there's a gut feeling that they're going to be quite extraordinary applications, and they're going to take computing enormously far beyond anything that we can imagine today. So it's really like setting the clock back to 1950. We're at the birth of an absolutely vast new industry. The state of evolution of artificial intelligence is like the state of evolution of the aerospace industry in 1910. It's got a long way to go.
We have the members of the Roundtable back to take questions and answers from selected sites throughout North America, South America, and Europe. Before we get to that, I'd like to remind you that in North America and South America, there will be another broadcast following this one. There will be a break for about an hour, and then a rebroadcast of a condensed version of our second satellite symposium, Knowledge-Based Systems, a step-by-step guide to getting started. Now, I'd like to inform you about the audience that you compose. There are over 1,200 downlinks worldwide, and our best estimate right now is that there are approximately 65,000 people watching this broadcast. There will be 2 question and answer periods because of the differences in time zones. Joining us for the first question and answer period will be the European downlink sites. Those questions and answers will be going through the control center in London, which is located at the Royalty Theatre, where we understand that it's standing room only, which is nice to hear. Coming through that site will be 11 call-in sites from various places throughout Europe. Now, on the panel here in Dallas, we have Doug Lenat from MCC, George Heilmeier from Texas Instruments, Herb Schorr from IBM, and Roger Schank from Yale University. Joining us from San Francisco are Alan Kay from Apple Computer and Edward Feigenbaum from Stanford University. Now, the first question we're going to take is from Washington, D.C., from John Roman. Go ahead with your question, please.
Hi, my name is John Roman, and I'm with LTS Corporation. My question is, what work is being done to make expert system front-end tools that don't require keyboard inputs and terminal text displays in order for the user to interact with the expert system?
What work is being done that for building expert systems that won't require keyboard input? Any comments on that? Roger, I would imagine you have some opinions on whether or not you'd want to do that.
Well, I'm a great believer in keyboards. I think that you can only communicate so well by means of mouses and icons, and then after a while, you really have no robustness in that kind of area. So commands that are simple can be done without keyboards, but commands that are complicated are either going to be done in natural language by keyboards or in natural language by speech. Speech is just way in the future right now in terms of long connected speech. So I think keyboards are here to stay.
We've got a comment from Ed Feigenbaum in San Francisco. Go ahead, Ed.
We at Stanford University, we at Stanford University are doing an experiment involving equipment from a company in Los Angeles called Speech Systems Incorporated to interface the Oncosin expert system for cancer chemotherapy advice to the speech understanding system.
Doug?
We also, at MCC, are doing a similar sort of multimodal kind of interface. The idea being that often when you're involved in something with text and a keyboard, if you have a different thing that you want to do, it often helps to use a different mode, such as speech or a picture coming up that you can point to. So we're working with the visual dictionary people, having thousands of images on screen as a very different sort of mode, and we also have a Kurzweil speech recognition and speech synthesis system so that we can enter commands that are tangential to the thing people are working on. So even though I agree with Roger that using speech as human beings use it to each other is a long way off, there's still lots of things that we can productively do today to use other modes than keyboards and online displayed text.
Alan Kay, would you like to comment on that?
Yes. I like speech also, but imagine trying to drive a car by telling every minute thing that you're trying to do to the car. Imagine trying to play music by describing what the music is supposed to be. We can only sing a single line of music, but we use our fingers to play much more complex pieces. So I don't agree that the manipulation by one's appendages is less efficient. I think in many ways it's more efficient if the context has been well set up.
Our next question comes from Paris, from Professor Kudratov. Go ahead, please. Go ahead with your question.
The problem of knowledge acquisition. What is the current status of automatic machine learning?
What is the status of automatic machine learning? Doug, I guess.
Machine learning has been undergoing a renaissance in the last decade. And by now we understand how to do a large number of fairly narrow kinds of automatic induction, automatic machine learning. You could analogize from that, for instance, to the way expert systems are able to get expert-level performance in very narrow areas. As for the general kind of learning that we usually refer to as children learning or human beings learning, that generalized learning is still a long ways off. And it's a long ways off because the more you know, the more and more quickly you can learn. And inversely, since our programs don't know much yet, they can't learn much right now. They can't learn by analogy, which is the main way that human beings learn. They can't learn by drawing on common sense knowledge because they don't have common sense knowledge. And I think until those two things are in, a broad knowledge base and a deep knowledge base, we won't have learning as we understand it in machines.
Roger?
I think computer learning is dependent upon the concept of case-based learning. In other words, what we are as humans are compilations of our experiences, compilations of vast numbers of cases that we have dealt with. And real experts are combinations of so many cases that are very particular that only they know about. And what they do to acquire expertise is they keep on gathering new cases by comparing current experiences to past experiences. In other words, they learn from their experiences. I think the idea that machines will be able to learn is a very far idea, very far in the future from the perspective of a business or a commercial application today. On the other hand, in terms of AI research, it's a very hot topic and it's a very exciting topic. So it is a very interesting AI research topic, but I wouldn't expect to see commercial applications immediately.
The next question comes from Boston, from Eric Brynjolfsson. Go ahead with your question, please.
Yeah, this is Eric Brynjolfsson at Foundation Technologies. Rule-based expert systems have traditionally relied on relatively shallow understanding of their domains. Do object-oriented languages provide the best method for building systems with a deeper structural understanding of their domains?
The question is, do object-oriented systems provide the best methods for deeper understanding of domains? We'll hear from Alan Kay in San Francisco.
Well, I'm not sure that it's good to make a distinction between the rule-based systems and object-oriented systems. Object-oriented techniques are really an architecture that a lot of different processing regimes can be used with. So I think in a way they suggest some pathways that you can take to making much larger structures that seem to be required by artificial intelligence. I certainly don't think that object-based systems are the end-all and be-all of what we're striving for. I think they're a way of dealing with certain kinds of modularity.
I disagree to some extent. I think that if you're going to have deep reasoning, what distinguishes that from shallow reasoning is that you don't simply have terms without connections to other terms, which is what shallow reasoning is, having rules with no connections to the terms referenced in the rules. As you begin to put those connections in, you begin to associate with the objects that they're talking about the connections to other objects. And so even if you don't start out calling it object-oriented programming, by the time you're done, what you have is something equivalent to that.
The next question comes from Dallas, from Anna Cedo. Go ahead with your question, please.
Yes, my name is Anna, and I work for Unisys Corporation. I was wondering, how do the Lisp machines exploratory programming compare to functional prototyping with fourth-generation language system and application generators?
How does prototyping with Lisp machines compare with prototyping with fourth-generation languages? Anybody want to take that one? Well, the view that I have, Alan Kay will answer that.
Well, most fourth-generation systems are ways of structuring things using a database to hold knowledge. And the difference really is the difference between a kit, which fourth-generation languages usually try to be, and with the toolbox that and the craftsman's shop that Harry was talking about. In many ways, for a person who's willing to become more expert, the tools available on the Lisp type of workstations are much more usable and available for quick prototyping.
Yeah.
Harry, I think the issue is one of flexibility and extensibility.
Any other comments on it? The next question comes from Munich, from Jordan Kasper. Go ahead with your question, please.
Hello, this is Jordan Kasper calling. The question out of the audience goes to Dr. Schorr. Why does IBM not offer dedicated Lisp architectures? And how does IBM view the portation of AI applications into their world of products?
The question is for Herb Schorr. Why doesn't IBM sell Lisp machines and board-level products?
Okay. The answer so far is that we look at AI as an ingredient of an overall transaction processing or other application. And basically it turns out to be a small part of the overall process. And so you want to add artificial intelligence applications to database transactions, to your standard applications. And so what we're seeing is that the number of cycles, if you wish, that you execute on the AI portion tends to be small in terms of delivery or production, in terms of delivery of a system to a bunch of end users.
The next question comes from Dayton, from Ted Taylor. Go ahead with your question, please.
One can see the potential for AI application. What is the best way to convince management to commit resources to it?
Given that you can see the potential for AI applications, what's the best way to convince management of the potential? Well, Herb, that's your job, isn't it? Don't you hit that?
I think the best way of convincing management tends to be to get started with an application which you know will have pay dirt, which will give you some results in a rather quick and short time. So basically do a good application for several hundred or under 1,000 rules, in which you can do it, demonstrate that it does something real for the corporation, provide you an ROI, provide you something that you couldn't deliver before. That we find is by far the best thing. Don't tackle something too ambitious, which has a high probability of failure.
George?
I agree with Herb. I think show and tell is really the best way to convince management of the initial impact of AI technology.
Our next question comes from Minneapolis, from Norm Santosky. Go ahead with your question, please.
Yes, we heard a great deal of valuable information this morning regarding Lisp. I'd be interested in what comments could be made regarding another language called Prolog. Thank you.
We heard a lot about Lisp this morning. How about comments about Prolog? Ed, would you like to comment on that? Ed Feigenbaum?
Well, I don't have a lot to say about Prolog. I'm not a Prolog user myself. Historically, Prolog implementations of expert systems have tended to be rather inefficient. I find that the knowledge representations in Prolog to be relatively opaque compared with the knowledge representations that I've seen in some of the better expert system tools that are designed on top of Lisp. I think the primary thing to keep in mind is that the implementation strategy is not a question of Lisp versus Prolog. It's a question of what higher level language, higher level than either Lisp or Prolog, are you going to use in which to cast your application.
I would like to add to that. I think basically what we see is that people like to program in a shell, basically, an expert system shell. And Prolog or Lisp essentially are the assembly languages. When you can't do the job you want to do in one of these shells, then you break out into Lisp or Prolog, or if your shell is written in C or Pascal or whatever it's written in, it's sort of like the assembly language. It's back where we were, if you wish, 20 years ago, where you couldn't do everything in your Fortran or COBOL, and you used assembly language to augment what you couldn't do in the shell. And that is also part of the answer to one of the previous questions as to why we don't have dedicated Lisp hardware.
That's also true for those of us doing research who don't use shells but are working from scratch. We tend to use Lisp not because the operations of the mind are somehow close to car and coder and cons, but because neither Lisp nor Prolog is very close to what we want to build, and therefore we choose something that has a good programming environment. And as Dick Gabriel and Harry showed in this morning's presentation, the 30 years of innumerable people building up that programming environment in Lisp make it still the best one for us to program in.
Well, one of the things that we didn't go into very much in that part of the broadcast was the advantages of Lisp for building shells, for building new languages in. And I completely agree with you, Herb, that if you've got a shell custom made for the kind of application that you've got, you're much better off. Well, one of the nice things about Lisp is it's a very good language for building those shells in. We have another question from St. Louis, from Tom Hehan. Go ahead, please.
Yeah, I wanted to ask about Prolog, but that's been covered. But maybe you could comment on some of the other AI languages that seem to be evolving, such as Nile, and maybe comment a little more about the role of Smalltalk in AI.
The questioner wanted to ask about other AI-oriented languages, such as Nile, I believe it was, and also Smalltalk. I would guess that Alan Kay has a few comments about Smalltalk. Alan?
Well, I think the strengths of Smalltalk are that it's object-oriented. It was actually the originator of the user interface that the Lisp workstations use, so it has a very good programming and debugging environment. It runs on quite a number of micros. There's a good one on the IBM PC. There's a good one on the Macintosh too. And it's a good way of getting started for doing quick prototyping. I think in many ways, even though I sort of consider that the Smalltalks have too much stuff in them right now, they have vastly less stuff than the Lisp workstation. So I think for a person getting started, it's an excellent way of going. I think the drawbacks on Smalltalk now are similar to the drawbacks on Lisp, in that in both the Lisp systems and the Smalltalk systems, there's been less provision made for actually delivering. Lots of people will, for instance, in a Lisp workstation environment, find some way of then translating the application to C, or trying to compile it in order to get it smaller and packageable. And Smalltalk suffers from that defect also. So I think of Smalltalk as a sort of a model object-oriented language, in that everything in it is object-oriented, and it's a good way of learning that style.
I'd like to point out that there has been a lot of attention given to the question of delivery on Lisp-based systems, both in terms of building or implementing Lisp systems on a variety of different pieces of hardware, and even developing new hardware. Here at TI, we've recently announced a new chip, which will, I would think, have an impact on delivery of Lisp-based systems. So there is work going on there. The next question comes from Milan, Italy. Lawrence Archer will be asking the question for Carlo von Diere, I believe is the pronunciation. Go ahead, please.
Yes. What developments are foreseen for using artificial intelligence in management training and education? What research is being done?
What research is being done in applying artificial intelligence to management training and education? Comments?
I think that the application of AI to training and education is now just getting started. There is a tremendous possibility, because of the advances in natural language processing, of doing education in an interesting way rather than a dull way. Previously, we've seen computer-based education, which has mostly been press button for next page, drill and practice kinds of things, very passive. And education really works if you're active. if you're in an environment and you want to know and you can ask a question, and that therefore means natural language. So now that we've been able to get natural language systems to start to work, we have begun to develop prototypes which allow the user to ask questions, to state hypotheses, to explore, to wonder. And I think that in the next 2 to 3 years, you'll start to see active educational systems which have a natural language component and a reasoning component in them.
The next question comes from Washington, D.C., from Dr. William Tafoya. Go ahead with your question, please.
Bill Tafoya, the National Center for the Analysis of Violent Crime at the FBI Academy. What micro-based products being marketed today as AI systems are viable? That is, which are both cost and performance effective.
What micro-based systems are being marketed today that are cost-effective? George?
I think a number of reviewers have singled out Personal Consultant, PC Easy, and tools that are available for both the TI and IBM PC as being some of the more powerful and productive tools for micros.
Our next question comes from London, from Mr. Carland. Go ahead with your question, please.
I must apologize to start on a rather negative note, but could members of the panel tell us about any failures in applying KBS technology to a particular problem? And what were the lessons learned in the particular case, and what are the wider implications for the technology?
Do we have some examples of failures? What are the lessons learned? Yeah, Roger, go ahead.
I think that it's often misunderstood about the nature of how you create new technology, and the assumption that we have been doing is building things which become automatic successes. I think the history of AI is a history of failures, and what that means is a good thing. What it means is that you're consistently building programs that you have to rewrite and change and adapt. Every system that exists today existed in some form or other in somebody's eye or on somebody's computer 10 or 20 years ago. They're constantly being revised and changed. So there are no failures in a sense. It's a different kind of philosophy of science. Everything is an experiment. Every system that you see today will be thrown out as being irrelevant and silly 10 years from now, I guarantee you.
We have a comment from Ed Feigenbaum. Go ahead.
Roger just addressed himself to the question of failures in AI research. I'd like to address the question to failures in expert system projects. The primary source of failures, I think, are two. One is failure to couple adequately to experts, and the other is failure to understand adequately the state of mind, the position, and the state of acceptability of your system to the end user. In connection with the expert, the main failure is to try to attempt an expert system without having the adequate time and commitment of an expert whose mental processes and whose knowledge base you're trying to model. Experts are people who are busy, and it's often difficult to command their time, but if you don't, you're almost guaranteeing failure in the project. The other problem has to do with the user, and that is if you don't understand what the conditions are under which your expert system will be acceptable to that user, you're going to have a technical success, but a technology transfer failure.
George?
I guess the failures that I've seen, failure in quotation marks, have been primarily due to people not planning for the update of the knowledge base, or not planning for the growth of the knowledge base in a smooth way.
Yeah, Herb.
Some of the failures are not in the sense that the project didn't succeed, but we wrote the expert system, and after a while it stopped being used. And the problem was that the problem chosen initially was really too simple. The new people in an area would use this expert system, and when they learned everything that was in the expert system, they no longer needed it. In other words, it was a great learning tool, but it didn't stay into use, didn't remain in use. So what we've sort of learned from that is you pick something with a large number of combinatorics, so that that's beyond, if you wish, what human beings normally can handle with a great deal of facility, or pick something that people don't do
very often, and you can find problems like that. Not something that someone becomes an expert in 3 to 6 months. Then the system will go into disuse.
We've got another comment from Ed. Go ahead, Ed Feigenbaum.
A classical source of the failure of expert systems is in making an assumption that you can proceed on a problem in an area in which the knowledge needed is much more extensive than that which is available. Remember, expert systems work well only in narrow areas of knowledge. And sometimes you think you're in a narrow area of knowledge, but in fact you need knowledge bases of wide scope. And then the whole project can come down and crash.
Okay, we have time for one more brief question. We're taking this one from Brussels, from Willie Arts. Go ahead, please.
Okay. What is the recommended background of people who will develop AI applications in a corporation? Is a specific AI education recommended?
What is the recommended background for people building knowledge-based systems in a corporation? Would you like to respond to that, George?
I think some of the more successful work, maybe it's not the most sophisticated work, but some of the more effective work has been done by people who had domain knowledge, who taught themselves by use of the tools to build their own systems.
Any other very brief comment?
Yeah, I'm not a great believer in the attempt of big companies to start out AI projects on their own. I think that you have to gain expertise in a university environment. I don't think it's possible to buy the tools and become an instant AI expert. Many people have tried that path. I don't think it's working that well.
I disagree with that. I've seen it work quite well in terms of applying knowledge-based systems. You can't do it to become AI researchers by just buying the tools, but I've seen many examples of successful systems.
I also think that there are a set of stages you have to go through. There's a stage where you believe that syntactic mutation, that random generate and test will get you the answer. And until you actually build a system and it fails, you're going to believe that. And so there are a set of programs everyone has to build, whether or not they get formal training in AI, until they get to the right mental set, I think, to do the next stage.
Okay, thanks. We're out of time for questions. I want to remind you of one thing. For those of you with one of these notebooks, please take the time to fill out the questionnaire, send it in to us, tell us what you liked and what you didn't like about the symposium. Remember, after a break in North America and South America, there will be a broadcast of a 90-minute condensed version of the second satellite symposium on knowledge-based systems, a step-by-step guide to getting started. And finally, I would like to thank all of those who have contributed to this, the third AI Satellite Symposium. In addition to the people you've seen on camera, I would also like to thank the many others who have worked behind the cameras. And thanks to all of you for joining us.